くりレ夢ムです。
ゆっくりマリサだぜ。
Hi, Raimo. Hi, Marissa. Hey guys. Let's learn about the relationship between the infinite and the finite.
ゆっくりしていってね。
Chapter 9. The infinitely small and the real line. Density and the continuum. Let's return to the real numbers and look more carefully at what the connection between the finite and the infinite looks like at the smallest scales. Between any two distinct real numbers, no matter how close together, there are infinitely many other real numbers. Not just a few, infinitely many. Pick any two numbers, separate them by any gap you can name, no matter how tiny, and the real numbers fill that gap with uncountable density. This property is called the density of the real numbers. It means, among other things, that there are no adjacent real numbers. You cannot name the real number immediately to the right of 0 because there isn't one. For any candidate you offer, I can find one closer to 0. The real line has no gaps, no jumps, no holes. It is continuous in a way that the integers and even the fractions are not. This continuity is precisely what makes calculus possible. The derivative and the integral are built on the assumption that you can take limits, that you can approach a point along a continuous path and ask what happens in the limit. If the real numbers had gaps, this would fail. The continuity of the continuum is not just a mathematical nicety. It is the foundation on which the entire edifice of physics is built. But there is a haunting fact about this continuous real line. Most of the points on it are numbers you will never write down, never compute, never name. A specific real number, pi, or the square root of 2, or a root of some polynomial, is something you can describe. But the vast majority of real numbers cannot be described at all. They are not the output of any formula, any algorithm, any finite sequence of symbols. They are, in a precise technical sense, unnameable. There are only countably many things you can write down and uncountably many real numbers. So most of them, almost all of them, in the sense that the exceptions form a set of measure 0, exist beyond the reach of any description. The finite world of language and computation floats, like a thin film, on an ocean of unnamed, unreachable real numbers. Chapter 10. Convergence and Divergence. When infinite sums work and when they don't, we have been moving between geometry, set theory, and analysis. Let's return to the question of infinite sums, because the distinction between convergence and divergence, between infinite processes that reach a finite limit and those that don't, is one of the most practically important boundaries in all of mathematics. The Zeno series, 1/2 plus 1/4 plus 1/8, continuing forever, converges. The total is 1. You can prove this in many ways, and every way confirms it. The infinite process reaches a definite, finite destination. The harmonic series, 1 plus 1/2 plus 1/3 plus 1/4, continuing forever, does not converge. It grows without bound, diverging to infinity. The proof of this is ancient and beautiful. Group the terms in blocks of doubling size, and each block contributes at least 1/2 to the total. Infinitely many blocks, each contributing at least 1/2. The total must be infinite. The difference between the Zeno series and the harmonic series lies in how quickly the terms shrink. In the Zeno series, terms shrink exponentially. Each one is half the previous. In the harmonic series, they shrink only as the reciprocal of the natural numbers, slowly enough that the sum escapes to infinity. This boundary between convergence and divergence is not a sharp line in all cases. There are series that sit right on the edge, so close to diverging that tiny changes in the terms tip them one way or the other. The Basel series, 1 plus 1/4 plus 1/9 plus 1/16, the sum of reciprocals of perfect squares, converges. Euler proved this and found the exact sum, pi squared divided by 6. That pi should appear here, the ratio of a circle's circumference to its diameter, in a sum that seems to have nothing to do with circles, is one of the most surprising and celebrated results in mathematics. The lesson of convergence and divergence is the same lesson that runs through all the topics we've explored today. Infinity is not a single, undifferentiated thing. It has structure. Some infinite processes are tame, leading to finite results. Others are wild, growing forever. The art of mathematics, and in some sense the art of understanding the world, is learning to tell the difference. Chapter 11. Gödel's incompleteness. The infinite horizon of truth. We come now to the deepest and most vertiginous result of all. In 1931, a 25-year-old Austrian mathematician named Kurt Gödel published a paper that shook the foundations of mathematics more violently than anything since Cantor. And its subject, at the deepest level, is the connection between the finite and the infinite, specifically, the infinite horizon of mathematical truth and the finite reach of any formal system. At the beginning of the 20th century, the mathematician David Hilbert, the same Hilbert of the Infinite Hotel, had proposed an ambitious program. He wanted to place mathematics on an unshakable foundation, a complete and consistent set of axioms from which every mathematical truth could, in principle, be derived. Complete, meaning no true statement would be left out. Consistent, meaning no contradiction could be proved. Gödel destroyed this program. Not just challenged it, destroyed it. His first incompleteness theorem states, any formal system that is powerful enough to express basic arithmetic, and that is consistent, meaning it doesn't prove contradictions, will inevitably contain statements that are true but cannot be proved within that system. Let that land for a moment. There are mathematical truths that no finite set of axioms and rules of inference can ever reach. The system is like a light in a dark room. It illuminates what it can, but the room is infinite and the light is finite. There will always be corners in the dark. Gödel's proof is a tour de force of self-reference. He showed how to construct, within any sufficiently powerful formal system, a statement that says, in effect, this statement cannot be proved in this system. If the system could prove it, the statement would be false, contradiction. So the system cannot prove it. But the statement is true. We can see that it can't be proved, which is exactly what it claims. True, but unprovable. The second incompleteness theorem goes further. Such a system cannot prove its own consistency. You cannot, from inside the system, prove that the system will never derive a contradiction. Trust in the consistency of mathematics must come from outside the formal system, from a meta-level of reasoning that is itself not fully formalized. What does this have to do with infinity and the finite? The formal system is finite in a sense. It is described by a finite list of axioms and finitely many rules of inference. The truths of mathematics are infinite, uncountably many, extending in every direction beyond what any finite description can capture. Gödel's theorem is the precise statement of the gap between them. The finite cannot capture the infinite, not through cleverness, not through more axioms, not through any formal method. The continuum hypothesis, which we discussed earlier, whether there is an infinity between the natural numbers and the real numbers, is an example of a statement that is independent of standard axioms. Just as Gödel predicted, mathematics arrived at a question it could not decide from its own foundations. And there are others. There will always be others. The incompleteness theorems guarantee it. Chapter 12. The infinite in physics and the finite in nature. At this point, I want to take a step away from pure mathematics and ask, what about the world? Does the physical universe contain actual infinities, or does it merely use infinity as a mathematical convenience? This is a question that physicists argue about seriously. In quantum mechanics and quantum field theory, the best physical theories we have, infinities arise regularly in calculations. The naive formulas often produce infinite results for finite physical quantities. The technique used to deal with this, called renormalization, involves a careful subtraction of infinities from other infinities to leave a finite, physically meaningful result. It is mathematically controversial but empirically extraordinary. The predictions it produces match experiments to more decimal places than any other theory in the history of science. Richard Feynman, who helped develop renormalization, called it a dippy process and hocus pocus. And yet it works. Whether this means that the infinities in the math are artifacts of the theory, placeholders for physics we don't yet understand, or whether they point to something genuinely infinite in the structure of reality, remains an open question. In cosmology, the question of whether the universe is infinite in extent is also unresolved. The observable universe, the region from which light has had time to reach us since the Big Bang, is finite and precisely measurable. But whether the universe extends beyond that horizon, and if so, whether it extends infinitely, is not something current observations can determine. Some models of inflation, the rapid expansion of the very early universe, predict an infinite universe. Others don't. What we can say is this: the mathematical tools required to describe the physical world are, without exception, tools that take infinity seriously. Calculus, differential equations, probability theory, quantum mechanics, general relativity, all of them rest on the foundation that Cauchy, Weierstrass, and Cantor built. The tamed, disciplined, precisely understood infinity that mathematics developed over 2 centuries is not just an intellectual curiosity. It is the language in which the universe has, so far, chosen to speak. Chapter 13. The second question. Before we reach the end, I want to ask you something that I think you might still be sitting with. Throughout this journey, we've seen the infinite and the finite entangled in every direction. A convergent series, infinite steps, finite sum. A fractal, infinite perimeter, finite area. Gabriel's horn, infinite surface, finite volume. Cantor's hierarchy, infinitely many infinities. Gödel's theorem, finite axioms, infinite truth. In every case, the surprise comes from the same place. Our intuition, built on finite experience, keeps expecting the infinite to behave like a very large finite. And it doesn't. It follows its own rules. And those rules, once you know them, reveal a kind of order that ordinary intuition never would have found. Here is my question. Does knowing this change how you see limits in your own life? The boundaries that feel permanent, the walls that seem to stop you from moving forward. Do they look different when you remember that a line can be infinite in length and still enclose a finite area? That a sum can go on forever and still come to rest? I'm not trying to turn mathematics into self-help, but I do think there is something real in this parallel. The relationship between what is bounded and what is endless is not always what it first appears to be. Leave your thoughts in the comments. I mean it. This one I'm really curious about. Epilogue. The bridge that was always there today, we have traveled from ancient Greece to the 21st century. We walked through the paradoxes of Zeno, the invention of calculus, the painter's paradox of Gabriel's horn, the fractal geometry of coastlines and snowflakes, the startling revelations of Hilbert's hotel, Cantor's diagonal proof and his hierarchy of infinities, the independence of the continuum hypothesis, the uncountable real numbers that cannot be named, the difference between convergent and divergent series, the quantum infinities of physics, and the incompleteness theorems of Gödel. All of these are chapters in a single long story. A story about whether the infinite and the finite are truly separate, or whether, as mathematics has discovered again and again, in ways that shocked and thrilled and sometimes broke the people who discovered them, they are not two opposing things, but two aspects of a single continuous reality. The finite is not the absence of infinity. The finite is what happens when you look at one piece of the infinite from the inside. Every line segment contains uncountably many points. Every moment of time contains infinitely many instants. Every bounded region contains an infinite structure of nested detail. The finite is, in a precise mathematical sense, built from the infinite. And the infinite, for all its wildness, is not unreachable. It is governed by laws. It has structure. Some infinities are larger than others. Some infinite processes converge. Some truths are unprovable. And within those constraints, which are not limitations so much as the shape of the territory, the infinite becomes something you can think about, navigate, and in some sense know. David Hilbert, who understood this better than almost anyone, put it simply, the infinite. No other question has ever moved so profoundly the spirit of man. He was right. And the remarkable thing, the thing I hope you carry with you from today, is that this profundity is not reserved for professional mathematicians. It lives in every coastline, in every piece of music, in every moment of time, in every act of adding numbers that never quite run out. Thank you for spending this time with me. If this video meant something to you, a like and a subscription help more people find their way here. And I'll see you next time. The infinite is closer than you think. Goodbye, goodbye, goodbye.